Okay, what's the answer? If you want to get newtons seconds per coulometers, all you have to do is multiply newtons per coulomb by seconds per meter, meaning you get volt seconds per square meter. Let's see how many got that. Yay. Nice work. So now, how do typical charged particles behave when they're in, let's say, a uniform magnetic field? Well, suppose we have a magnetic field B, which is pointing out of the screen here. So it's the same everywhere in the screen. Here's our charged particle. Let's give it a velocity to the right. Well, let's do our right-hand rule. B is that way, so our fingers go that way. V is that way, so our thumb goes that way. There's a force in the downward direction, perpendicular and always perpendicular to the velocity. By the way, does this magnetic force do any work on the charged particle? Trick question. If you have a force that's always transverse to your velocity, will your velocity ever increase or decrease? No. It'll just go in a circle. This is simple circular motion, which you dealt with in Physics 7b. And we remember that the force needed to keep an object going in a circle is mv squared over r. If you review your Physics 7b, you'll find that. We're just going to set that equal to the magnetic force now, q times v times b. And if you do that and then solve for the radius, you get m times v over q times b. Do you remember what m times v is? That's the momentum, right? So it's related to the momentum of the charged particle. The bigger the momentum, the bigger the radius. Now, if in addition this particle had some velocity out of the screen, it wouldn't feel that. That component of the velocity wouldn't be affected by the magnetic field. And what you would have is a charged particle would undergo a motion like this. It looks like a spring, or mathematically, that's the form of a helix. That shape is called a helix. So in general, what you find is that charged particles moving in a magnetic field move in helices around the field lines. The stronger the field, the tighter the helix. Now, that actually turns out to be another reason why life on Earth is possible. And we have to go back to the surface of the sun. The sun itself, of course, is this giant ball of gas, and in the center there are nuclear reactions happening which give the energy that's coming out of the sun. That energy heats the material deep inside the sun. There's a plasma, and again, magnetohydrodynamics comes into play, and you get a very complicated magnetic field for the sun. And the field at the surface of the sun is quite strong. And right at this point, for example, you can see that there are charged particles coming out of the sun, arcing around, and going back in. There are these giant loops that can form. And sometimes you can see them on the edge of the sun. If you go to the website for the Solar Dynamics Observatory, which is a satellite in orbit far away from the Earth, it looks at the sun all the time and takes pictures. You can just see the current solar weather, which is kind of fun. Every so often, though, and especially during the maximum of the solar cycle, you can get very large ejections of material from the solar surface called coronal mass ejections. And that can send billions of tons of stuff streaming toward the Earth. The stuff is basically high-energy particles. It's a plasma, so electrons and protons not combined. And it's fairly high energy and streaming out at about 1 million miles an hour from the sun. So after you see one of these solar flares, you'll get an alert from the Solar Dynamics Observatory that a certain class solar flare is detected. And if it happened to be pointed straight at the Earth, that is along the equator of the sun and aligned up with our line of sight, a couple or 3 days later, that material reaches the Earth, and you can get aurora borealis and so forth. Now, that can cause electronic interference and so forth. And we've just passed the maximum of the solar cycle, which we call solar max. It happens every 11 years. The previous one was in 2003, and early last year was the maximum of the last one. Now, this picture shows what's going on. The Earth is not this close to the sun. If we were this close to the sun, the oceans would boil and we'd be cooked and we could forget about it. The Earth is 150 million kilometers away from the sun, which is about almost 1.5 million kilometers across. So, nevertheless, if one of these solar flares occurs and it shoots a whole bunch of charged particles at the Earth, once they reach the Earth, they tend to spiral along the magnetic field lines. Some of them get sent into the poles of the Earth, either to the north or to the south, and you can get this phenomenon that we call the aurora borealis. The Earth's magnetic field is basically shielding us from most of the charged particles. Some of them get in, but most of them get deflected out away from the Earth. If it weren't for the Earth's magnetic field, we'd have a lot more problems with radiation coming from the sun. It might make it actually harder anyway, for life to survive. I did get to see the aurora once. I was on a flight from Chicago to Sacramento. I was sitting on the right side of the airplane, and it was night, and it was in 2003. And I'm looking out the window, and I see this green glow in the sky. And then I realized it looked like curtains, and the curtains were sort of waving and changing color slowly, and I was just mesmerized. I must have stared at it for close to an hour. Absolutely beautiful. It's worth a trip to go try to see it, maybe up in Alaska. If you want to go during the winter, you can't see it in the summertime. I was in Alaska last summer, and I really wanted to see the aurora, but so I waited up really late. It never did get dark at 1 in the morning. At night in Alaska in July. So there you go. Now, I know you all have a lot to worry about in your lives, right? With all the different things happening to our Earth, deforestation. We're in the middle of the 6th great extinction on Earth, climate change, and so forth. Let me add to your list of worries one other thing. The Earth's magnetic field, which you saw was this complicated mess, right, inside, every so often undergoes a field reversal. Maybe every few thousand years. We don't know what causes it or how often it cycles. There is a scientist here at Davis in Earth and Planetary Sciences, Professor Veresub, who studies this. And what he does is he measures what we call paleomagnetism. He finds old strata which preserve the magnetic field strength and direction from when that strata was created. Let's say from a flow from a volcano or something like that. If there's iron in the strata, they can capture the magnetic field. So what he drills down, finds cores, takes samples, dates them, and then measures the magnetic field. And it has this nice map in time of what the Earth's magnetic field looks like. One of the things he discovered is that the Earth's magnetic field can change pretty quickly in decades to a century, something like that. It can flip from north-south to south-north. And what has happened during at least my lifetime is something called the South Atlantic Anomaly of the Earth's magnetic field. And there's this growing patch in the southern hemisphere of the wrong kind of field lines coming out at that point. And it is changing. It is growing. And we don't know for sure, but the Earth could be undergoing or in the beginning stage of a major field reversal. Now, why is that something to worry about? Well, that will basically be like Captain Kirk saying shields down on the Enterprise, because all those charged particles are then going to start cooking us on Earth if the magnetic field goes through this jumbled near zero state. So, okay, at least it's not something that, we did to ourselves, like climate change. All we can do is find another planet, I guess. So here's the second right-hand rule you need to learn, okay? Imagine you have a current, and the current's in a wire, and it's coming out of the screen in this picture. You can tell it's out of the screen because these circles are cut on the back side of it and not cut on the front side. We're going to take our hands and put our thumb in the direction of the flow of positive charge, which is the direction of the current, grab the wire basically, and then your fingers tend to wrap in the direction of the magnetic field lines, which are circles, which do that. They are coming out of the screen. So this is like, I should do it like that, right? Hold my hand like that. You could hold your hand up with your thumb like that to get it. If you look down the wire, the current coming at you, the magnetic field lines are circles that look like this, surrounding the wire. Now, if you think about it, because they're anywhere along the wire, the magnetic field lines form sheets that go around. And the tighter the concentration of field lines, the stronger the magnetic field. I can tell you it tends to be 1 over the distance from the wire for a long, straight wire, but we won't actually do that calculation ourselves. So, to see if you were paying attention on the last slide, let's do a clicker question. So we have 2 long, straight, parallel wires carrying current. One is coming out of the board on the right, and one is current is going into the board, into the screen on the left. So use the right-hand rule and determine the magnetic field at a point halfway in between. Does it go up, down, left, right, or is it 0? Go ahead and discuss. Make sure you use your right hand, not your left hand.